So good morning, everybody. Welcome to this Invisible School 2021. So I'm Luca Merlo from the Institute of Theoretical Physics in Madrid, and will chair these lectures. But before starting with the lectures, let me introduce Silvia Pascoli, who is the PI of the Hidden Network, and she will open officially the school. So please, Silvia, go ahead.
Good morning. So I want to give you a welcome. This is the first event we organize at the network. So I'm going to show you just a few slides to welcome you to the Hidden School Online 2021. So let me share my screen. It should work. There we go. Okay, so as I said, this is kind of the welcome because it's the first activity we do as a network. And it's the Invisible School 2021. As I will explain you just in a couple of minutes, each year we organize two main events. One is the school to train our kind of young generation, and the other is the workshop in which we meet together with the ESRs, the PhD students and more senior people within and outside the network. To discuss various topics of physics. This is the outline of the school that I'm sure everybody of you knows, but I take this opportunity to thank the lecturers and the tutors that are going to pass some time with you and explain the physics that we like so much excellently, as I'm sure they will do. And this week, I want to start thanking Veronica, which I'm sure will give you fantastic lectures on the Standard Model and Higgs physics. So this is our network. This is an ITN funded by the European Union and started last October 2020. And I think this summarizes really what we are. We're just a bunch of physicists who really like to discuss physics together and collaborate. And the focus of our research is the hidden universe. And this is kind of what inspired us, that what is essential is invisible to the eye. And this is what we search for in our research. The focus is on asymmetries in all their kind of configurations, going from lepton number and baryon number explaining the baryon asymmetry, going to CP violation, neutrino masses and neutrino mixing, to axions and hidden global and gauge symmetries, dark sectors, dark matter, and BSM physics. So the scope of the network is very broad. And we are also a very large kind of number of institutions. We have 13 beneficiaries from 5 EU members in an associated country, and 25 partner organizations, which includes leading labs like CERN, Fermilab, and the University of Tokyo, as well as 15 leading universities in all continents, well, except Antarctica. Really, we go from Australia to the US to Asia, from Japan to India to China to South America. And so we are very, very broad kind of number of institutions and scientists involved. We are also 7 private sector enterprises, 5 focus on technological research and 2 on science communication, including El País, who is one of our beneficiaries. So we are roughly a network of around 100 scientists. And this is the list of the beneficiaries, at least as it stands at the moment, but we are in the planning of including one more beneficiary to this. And this is the list of our partner organizations, which add so much to the research and the atmosphere of our network. As I mentioned at the very beginning, the network school is a key activity because this is when we train together. And each year we organize an ITN school. Usually we do it in person, but of course, given the circumstances, this year is going to be online. And I want to thank UAM for organizing this school this year. And this is really the glue of our network, our ESRs, and we are very proud and happy to have them, and they are all in the audience. We have 6 ESRs who are already joined the network last fall. 4 will join soon. So we have Gioacchino Piazza, Mario Fernandez Navarro, Federica Pompa, Valentina Montoya, Virgil Dandoy and Francesco Costa. And then the ones who are going to join soon are Maria Ramos, Patrick Bolton, Salva Rosauro Alcaraz, and Giacomo Landini. And we are actually in the process of hiring 4 additional ESRs. And so by next fall, we will be nearly at the full kind of composition of our ESR team. So with this, I don't want to spend more time, take away more time for the lectures that Veronica will give you. So I just want to thank you very much, especially the non-network members for participating in this school. So I wish you a very good time during these lectures, and I invite you to join us for the Invisible 2021 workshop, which is going to be organized by UAM online again at the end of May, beginning of June, and you can find all the information on our website, and the link to the website is actually given here. So thank you very much, and thank you, Luca.
Thanks to you, Silvia. Thanks for the presentation of the network and the introduction to the school. Actually, you made me a favor because you already showed the schedule of the school. Let me just remind you that the school is also broadcasted in YouTube. So if you want to see again the lectures, you just go to YouTube channel of the Invisible School and you can find there the lectures. And say that, I think that we another important message. If you have any question or comments, you can write directly to me, because I'll be the host during the lectures, and I will try to bring up all the questions or the comments to the lecturers whenever it is possible to do it. So without any hesitation, let's go to the first lecture. So please, Veronica, you can share the screen and start the lectures as you wish. Thanks a lot.
Thank you, Luca. That's right. Okay, let's start here. Cool. So you can see my slides, right? You can see my screen? Fantastic. Yes. All right, so I've been asked to give these lectures on the Standard Model and the Higgs mechanism, and I assume many of you already know that there is a Standard Model. Because you're attending this school, you're probably most interested in these open questions that the Standard Model has left. More than, let's say, the structure itself of the Standard Model. But as you can imagine, you need to understand first how the Standard Model works in order to make, things that are beyond the Standard Model. So what I thought I would give you during these 6 hours or a bit less was a bit of a more in-depth study of the Standard Model from the point of view of what makes it so successful. And the success of the Standard Model relies a lot in the context of symmetries, okay? So my lectures are not going to be about computing QED at one loop and whatever. They are going to be about trying to find the underlying structure of the Standard Model. Okay, so you probably are familiar with this kind of depiction of the Standard Model, where essentially what you are told is that the Standard Model is very simple. It's made of elementary particles. The matter content of the Standard Model is quarks and leptons. And from each of those, we have 3 families, 3 generations, right? And you are also told that the interactions that the Standard Model can explain are given by these force mediators, the gluon, the photon, the Z and W bosons. And you probably also heard that the last missing piece of the Standard Model, the Higgs particle, was discovered recently in 2012. And since then, we've been looking for the characterization of this particle, the Higgs. Okay, so it's probably all these, let's say, popular science things, you know them already. You probably know as well that the Standard Model is not the last thing, it's not the last word, and it cannot explain a lot of the important things that are happening in the universe. And that's why you are in this school, right? You are in the hidden school of things that are not understood and not seen. We know that the Standard Model can be it because from starters, most of the universe is made of things that are not the Standard Model. You've probably seen this kind of plots as well, where the energy matter content of the universe is shown, and where most of the universe right now is made of dark energy, which is something, a kind of substance that is creating more and more space and accelerating the universe. You know that about a quarter of the universe is made of dark matter. And this is probably a new type of particles of new sector beyond the standard model that is responsible for such important things as our existence, right? The fact that there are galaxies, and in galaxies there are systems and planets where we can live and so on, is due to the presence of dark matter. And we don't know what dark matter is. So all this is hidden parts of the universe, most of it, the dark universe that we do not understand, and the standard model cannot explain. And the part that we can, to some level, understand is this, mostly hydrogen that you find around in the universe that makes up for the visible matter. There are, this is one thing, it's quite important. Most of the universe, we don't know what it is, and the standard model can't explain it. But it's not the only thing that the standard model is unable to tell us. For example, it's true. Now we have this last missing piece of the puzzle for the standard model, which is this Higgs particle. But the quantum nature, the existence of a light scalar is something that at a quantum level is really difficult to understand. So how we can have a light quantum scalar is something that is really theoretically complicated to understand. And that has led to a lot of theories beyond the standard model trying to link the presence of the Higgs with new sectors beyond the standard model. But there are many other things that we know they are there and we don't understand. For example, we know there was an early phase of the universe, probably led by inflation and then a process of reheating that, of course, is not explained in the standard model. We don't understand the quantum structure, again, of the QCD vacuum. And maybe behind this, there is a new light sector made of axions of other light particles that could, link new forces, if you want, to the QCD sector, the sector of strong interactions. Another, very firm evidence that the standard model is not the last answer is the fact that we are surrounded, we are made of matter, we are made of atoms that are made of protons and electrons, and not antiprotons or positrons. And although the standard model makes some distinction between matter and antimatter, this is by far not enough to explain the huge asymmetry between matter and antimatter that we do see in the universe. Of course, I talk about the forces of the standard model. I was showing you the photon, the gluon, the Davion cell bosons. Those explain 3 of the 4 forces of the universe that we see and we experience. But gravity is still a mystery at the quantum level. Can we incorporate gravity in our quantum field theory? A very successful framework, still an open question. And then there are lots of different issues that are not explained by the standard model. For example, why there are 3 families, why this particular structure, why not something else? The masses that we see, the way the particles coupled to the Higgs are, completely, it looks from outside as very random, right? The structure is very hierarchical. And all these things seem to call for an explanation. Okay, so yes, you are here, you're in a hidden school trying to actually study things beyond the standard model. And here there is like a snapshot of the many reasons why you are here. But there is something there that we need to evaluate. And what we need to realize is that despite the standard model flaws, as a framework to explain the universe, what we see, early universe, and so on, when we go here on Earth and in space, and we look at the behavior of particles, of these particles we look over here, that behavior is very, very well explained by the standard model. The best laboratory you want to examine at high precision the you want the behavior of the standard model particles, is currently the Large Hadron Collider. You know, this CERN experiment that has been running since, 2011, and there is a lot of data taken and analyzed and so on. And what the LHC is doing is searching for new physics, of course, but it's also probing the properties of these standard model particles to a very high precision. So if the standard model is not the end of the day, let's say if there is something beyond the standard model, and we have this high precision machine looking into the intricacies of the standard model, maybe the LHC will tell us something beyond the standard model. It will give us a hint that there is something going on. To that, what the experiments do is from time to time, they give the public a kind of summary plot of what is the status of our understanding of the standard model coming out of the LHC. And you can just Google, for example, ATLAS or CMS, the two experiments at CERN, public results. And you could see plots like this one. Those are summary results. The CERN, the Large Hadron Collider, has gone through several phases of different energies at which they were colliding protons. They started with 7 TeV. They moved towards 8 TeV. And in something called run 2 of the LHC, they have been colliding protons at a higher energy, 13 TeV. In the next run, they will probably go up a tiny bit to 14 TeV. Okay, so they are just colliding protons to very high energies, and at different stages, they go and crank up a tiny bit more the energy. So these kind of plots, what they show is what is the probability of interaction among these protons to lead to a particular final state. So for example, what is the probability that when two protons interact, they produce a W boson, or a Z boson, or a TT bar pair, or for example, A Higgs. This probability in the collider language is measured in terms of picobarns of a cross section, whose units, typical units, are picobarns. Sorry, yes, exactly. You see that this scale is logarithmic. There's even here they do a cut from 10 to the 6 to 10 to the 11. So as you go in this direction, you are going to things that are more and more probable. So that when protons collide, they produce a lot of the time these kind of processes, and very few times they will produce these kind of processes. So when you go from top to bottom, what this plot is showing you is the kind of things that happen at the Large Hadron Collider and how often they happen in a logarithmic scale, meaning that we are talking about from highly probable to tiny probability of something happening, okay? And meaning that this is, for example, production of a single vector boson, W or Z or TT bar, is quite, common. So since the beginning of the Large Hadron Collider, the experimenters have been measuring this and this and this and collecting more and more data, whereas things that are a bit more complicated, for example, two massive vector bosons like the W's is a bit less probable. The Higgs took a little bit more time. Until 2012, it wasn't discovered because we needed more and more data. And as you go down, you get things that are more difficult to produce, less probable, more tricky, and but now that they are already being measured. That's what they appear here. For example, 4 tops are being produced. Remember that the top is a very heavy particle, is the heaviest particle we have in the standard model. So to produce 4 of them, it requires lots of energy, and it requires a lot of collecting data in order to be able to observe it. All right, so why am I showing you this? I know that sometimes these plots from experimentalists, especially from the Large Hadron Collider, can be quite overwhelming because they have so much data and they want to explore all possibilities and they want to then summarize everything, that, you know, sometimes you feel like vomiting after that many, you know, slide after slide after slide. And, you know, sometimes we don't pause and think of what this really means. And this kind of summary plot shows you a snapshot of how well nature, which is what we observe at the Large Hadron Collider, agrees with the standard model expectation. Here we have measurements. These are the color things at different energies. So you are really reaching different kinematic regimes and measuring things. So this is a measurement of what nature is doing. And the gray bar corresponds to the theoretical prediction, where theory here means the standard model. This, if you want, rubbish theory that is unable to explain most of the universe, yet when you look at many, many different final states, not just these ones, but hundreds of final states, very delicately, with high precision, the agreement between nature and what the standard model says is excellent. Okay, so for example, you take a ratio between data, so what nature is telling us, and theory, what the standard model predicted, everything lines up around 1. Okay, so this is telling us that the standard model cannot be right ultimately, but it seems to have many components that are correct. That despite we know that probably there is something influencing the way particles behave at the Large Hadron Collider. Probably we think that there must be some new physics around that scale and at high scales to explain neutrinos, to explain dark matter, and so on. When we look at high precision, so far, we have seen no deviation. And I believe this is very much due to the fact that the standard model is based on very solid principles of symmetries. The structure of the standard model is very successful. Our predictivity, our ability to compute to high precision these gray bars, if you want, is very much due to the symmetry structure of the standard model. Okay, so what I'm going to give you in this course is a view of the standard model from a symmetry perspective. Why? Because you can take these lessons, the way the standard model works, we built it, well, the people behind us, before us built it, built a very successful framework that is being hammered every day by the experimentalists at the Large Hadron Collider and many other experiments, trying to find something beyond the standard model. And this structure, the standard model structure, is still standing. And a lot of it has to do with this robustness due to symmetries. Okay? Great. So with no further ado, I'm going to start, talking about the structure of the standard model. Let me see if I manage to do this. Perfect. Fantastic. By the way, you tell me if at any moment there is any issue with sound or you don't see something, okay? Luca, you will tell me. Right. So I've shown you the typical snapshot of the standard model. They tell you, okay, this is the matter content of the standard model, leptons, quarks, force mediators, the Higgs. Sometimes you even get t-shirts of mugs that tell you that the standard model is very simple. It has this Lagrangian, where, for example, you will put some kind of electromagnetic or force interactions, then you might put some stuff like this, kinetic transfer fermions, then you might put some Lagrangian for the Higgs or kinetic term, plus some potential for the Higgs. You've probably seen this kind of t-shirt, no? And for us, it's like, wow, look, we can explain the universe with a line of a Lagrangian. Right? Or sometimes, instead of this, before this Lagrangian form became so popular, we also had this way of introducing the standard model as saying, standard model, very simple, is this, is SU3 cross SU2 cross U1. That's the standard model. And that was like the snapshot of what the standard model is. In both cases, what you are doing is equivalent. It's saying that the standard model is based on some assumptions about the matter content and the forces that will intervene among the interactions of this matter content. And those interactions and the presence of these forces will be related to particular symmetries. In this case, SU3 cross SU2 cross U1. These, as you probably know, those are gauge symmetries. Okay? And with that, we feel very, let's say, powerful, because with very simple, with a line, you can explain the universe. But we know this is not true. We know that actually we do these kind of things because indeed, after all the complexity we see in nature, all these particles, all this behavior, and so on, to understand that behind this there is a very simple symmetry structure is really amazing. I'm going to walk you through some of the steps to get to that point where you say the standard model, most of what's going on in the standard model can be explained in that line, with that line. I declare this is the line, and then I can explain a lot of the things, most of the things that are seen in the Large Hadron Collider. Okay? So I already spoken about symmetries. This SU3 cross SU2 cross U1 is just a statement about a particular type of symmetries, but the standard model is plagued or based on a lot of symmetries. So before we get into the structure of the standard model itself, I want you to think about something. You probably went from the stuff when you were in high school, let's say, you were told about Newtonian mechanics, right? They told you stuff like if I take an object of mass m and I apply to this object a force F, it will experience, that object, a change in their movement, an acceleration that will be proportional to the mass, right? And you also probably were told about the force, the gravitational force, that has to do with the masses involved, is inversely proportional to the distance, and so on and so forth. No, you were told about laws of physics that you won't dictate how, given a particle, so an object of mass m, is going to react or experience a force applied to it, or how two objects with mass m and m prime, how they are going to interact with each other. And at some point, maybe not in high school, but later on at university, you were told about the concept of, instead of talking about forces, which is something you can think and understand because it's like something that a human will do, is to push something, apply a force. It has a physical, intuitive meaning. You went a step ahead, and then you were told about the presence of fields, right? You, instead of thinking about a force between two objects, you will kind of start developing a concept of a probe charge or a probe object of mass unit. And then you will talk about how one object of mass m is changing the environment, so that if I introduce a mass, it's going to feel the presence of that object. So you went from a very human-oriented term, which is force, to something a bit more abstract, right? And then you were also, based on this intuition as well, then you started learning Maxwell's equations, right? and Maxwell's equations that had to do with the electric and magnetic field and how these equations actually mix both and so on. Later on, you were also told about special relativity, where they told you that actually all Newtonian mechanics is not wrong, but it's not the final answer. There is a bigger framework that embeds Newtonian mechanics, and this is special relativity. And there you realize that actually the concept of space and time, which again for a human is completely different, right? In the context of special relativity, there was something more abstract, beyond our, let's say, human intuition, which was you wanted the network of space and time, and how space and time don't have any meaning by themselves anymore, and actually you change coordinates, what you call the space or time changes, and so on. So you went from always, let's say, like a baby doing steps when you crawl, and then you start moving, you walk, and at some point you start designing an airplane and you are able to fly, and then a rocket and so on. You went from very simple, very close by concepts to things that were more and more abstract. Okay. And after special relativity, you were told about general relativity, you were told about quantum mechanics, which again went beyond your usual intuition. And then you were told that special relativity and quantum mechanics are inconsistent, so then you were told maybe about quantum field theory that unifies all these concepts. But still, going more and more towards the area of more remote and more farther from the usual human intuition. And I know it's been a long path, right, of learning from high school to getting a bit more this scientist way of thinking about things, this empirical way of viewing nature, to the point where you are able to compute to high precision important things, for example, in QED. It's been a long path and a very quick path as well, that for humans, for humanity, took maybe centuries, and for you had to take 4 or 5 years. Okay? But I want you to step back for a second and think, okay, so I've been told about quantum field theory, I've been told about Maxwell's equations, I know about Newtonian mechanics, I know these things work. And usually the way we explain these things are, we try to get more and more abstract, but there is always some assumption, some way of introducing the laws of physics that are as a given. For example, when you were told that Newtonian mechanics was this, that this is the equation of motion, you spend a lot of time just trying to understand what it means, a lot of time integrating it in all the different situations, like throwing an object, blah, blah, blah. And probably at no point you were thinking, okay, so F is equals ma, but why? Where does this come from? Like, I know that Newton or Galileo or scientists of that period, what they had to do is go and measure nature. That was already a step, empirical science. And through these measurements, they deduced that equation. This is a second order differential equation. Typical, or a differential equation is a typical thing that happens in nature, an equation of motion. Why is there this equation of motion? Why? What is the reason why nature behaves that way? What makes nature depend on mass the way it does? Or it has in the equation of motion a second derivative with respect to distance? Why? And the things became even more complicated when you started doing electromagnetism. I don't know about you, but in general, I taught electromagnetism many years, and it's one of the hardest subjects for undergrads. Why? Because there is so many things that you have the 4 equations, you need to understand all the different situations and integrate and so on and so forth, that the students are just given these 4 equations in the most general form, and you spend all this time as an undergrad just trying to use them, to understand what they mean and to use them, and that's it. But at no point, you probably, you were like, why is like this? Why is one of the questions is like this, or why I have another question that goes like this? Why? I mean, I understand that Maxwell, you probably understood that Maxwell went, measured, and observed that kind of behavior. You also know that these equations are consistent with principles that you learned afterwards, like, for example, special relativity. You know all these things, but why are these equations the way they are? Like, what is the ultimate reason why the electric and magnetic field follow that kind of equation? Why do they depend on the presence of charges that way, and so on? Right? We already had enough scratching the surface of these equations. It was already quite an achievement for humanity to just obtain these equations, understand that from what seems to be at the first sight always something very complex, we physicists tend to try to find a unifying way of looking at it, and then find an equation, a mathematical expression that predicts to some extent what's going to happen. Those equations of motion, those are already quite an achievement. What I want to tell you is that actually all these equations, everything you learn are a consequence of imposing asymmetry, or if you want, are a consequence of realizing that is a higher concept, even a more abstract concept, that is the concept of symmetry. For example, you've been, again, spending lots of time talking about Lagrangians. Yes, learning in mechanics about the Lagrange-Euler equations, and based on that, you explain or try to describe systems. Or Hamiltonians, when you go to quantum mechanics, you go from one to the other, and so on and so forth, okay? And with those, you obtain equations, you define a Lagrangian, and then with that, you are going to obtain an equation. For example, you could obtain F equals ma, or the fact that the electric field depends on the composition of charges, and so on, right? But actually, all these equations of motion, or this description of the behavior of the objects, is actually a consequence of asymmetry. Okay? And this symmetry is not at the level of force, mass, acceleration, so position, velocities, times, or distribution of charges, or something else. These symmetries are something that are that come from studying something beyond the Lagrangian, beyond the Hamiltonian, a higher object that you probably also heard about, that is called an action. Okay? This action, a dimensionless quantity, is behind all the behavior that we see, all the equations of motion that we see, and so on. We know that the action is precisely defined to say that what happens, the reality, or what happens more often in the case of the quantum world, will be situations where the action is minimized, with the variation of the action is minimum. Now, if the action has any symmetry, any kind of invariance under transformations, this is going to change all the laws of physics that we get afterwards. So in particular, when we do this variation of the action and we set it to 0, with that is how we get these equations of motion. all right? And the action depends on what we want to describe. If we want to describe a particle and its behavior with a space-time, we will have an action that may be as simple as something that goes as an integral over the space-time interval. This is ds, is the typical dt squared minus dx squared, okay? And this action by dimensional analysis is going to be actually proportional for a particle to the mass, and then you probably need some kind of c instead. Why is the action for a particle propagating in space-time given by this particular interval? It's simply by saying that you want nature, or you believe that nature cares about the invariance, the symmetries of space-time. In the case of space-time, we are talking about a particular set of symmetries. This is something I'll explain later on. That is SO3, 1, a particular group of symmetries. And then you say, okay, if my action is going to be invariant under these symmetries, there is only one object that I can write that is invariant, and it's that one. Okay, this one, particularly this one. Well, so once you say my action has to be invariant under space-time symmetries, and I want to describe a particle of mass m propagating in space-time, this is the form that the action can have. Well, so starting from that particular form of your action, you are able to obtain special relativity. All these famous, Lorentz transformations and so on and so forth, and the equations of motion of a particle in special relativity can be obtained through this S, this particular form of S. And if you make the limit where the velocity is very small, of this particle is very small compared with the speed of light, then you recover Newtonian mechanics. So we get special relativity and we get Newtonian mechanics. Same goes for the forces. The forces in the standard model that we know of, they are also based on principles of symmetry. For example, if you say that there is a local, you believe that there is a local symmetry, let's say U1 symmetry. Let's say that this is the electromagnetic U1. You impose that in nature, there must be a local U1 electromagnetism. The only action that you can write that describes precisely this type of behavior is something that goes as an integral of a space-time of this object that you know already. The factor in front is not important, obviously, but this f mu nu is the only object you can write that is consistent with the behavior you expect of an action. It has to be smooth, it has to go to zero at infinity, it has to be, that leads to consistent equations of motion, to ordered second order maximum and so on. If you just say this and say that there must exist a local U1 symmetry in nature, you get precisely from this action Maxwell's equations. All the Maxwell's equations, okay? So far, you've been told this is the Lagrangian of the standard model. This is the matter and energy content of the standard model. Those are the interactions we write down. If you have a Dirac fermion, this is what you write down. If you have a Majorana fermion, write down this other thing. But all these things, all this is a manifestation of the presence of symmetries. And those determine the Lagrangian of the standard model and determine the kind of behavior and interactions that you will expect. So having said all this, it's a lot of that's fine. It's the most important thing. The rest you can get from books, right? You can always go and look at the interesting books. Like, for example, I'll give you a few references in a second, but to be aware that many of the things that we have been told from day one in high school in physics are actually a consequence of something that is much more abstract and much more demoted from our everyday experience, which is the presence of a higher object, the action, whose minimization leads to what we are able to see, the possibilities we see, and that this action admits or can feel or not feel, can be invariant under that some symmetries is actually leading to all the things we know, to the behavior of our Lagrangians that we write down, our quantum field theory, and so on. It's true that we don't go through all these steps because it's much more convenient to simply say that in quantum field theory it's convenient to write a Lagrangian, and then when you have a Lagrangian, you have Feynman rules, and we have our way of doing things that is well established, right? You do the Peskin-Schroeder, you know how to compute things. But we forget that actually all these have been determined by the presence of symmetries in an object called an action. Okay, so symmetries do play an important role in determining the standard model structure. Anything you do beyond the standard model is going to also be relying on some level of symmetricity, okay? It's true that often when we do beyond the standard model, what we do is we do models, we build models where we say this is our matter content, this you determine the particles where is their transformation properties under certain symmetry groups, and that determines their behavior. So when you build models, you are going to take into account this symmetry all the time. And think that this is the same for the standard model. It's what makes it so successful. So we are going to dwell a bit more deeply into this concept of symmetry. Okay, so symmetries. I've been talking about symmetry. You, again, as a human, you already have an intuitive way of thinking about symmetries. For example, you can think on simple reflection symmetries where you think the face of a person tends to be symmetric, where we have one eye in one side, the other has the mouth, and so on. As you also know that the symmetries in our everyday experience are rarely exact. People's faces are not exactly symmetric, otherwise they would be weird and very strange to us. You also have intuition about rotation symmetries, right? You take a ball, you turn it around in all directions, and it's still the same ball. And if it doesn't have any kind of features inside, let's say a blue ball, you move it around and you show it again, and there is no way of distinguishing it. So symmetry is intuitively an invariance, meaning things stay the same if I do transformations. Now, these transformations, these symmetry transformations can be done at two levels, if you want. Those can be external transformations. For example, I can take a quantity, let's say any quantity, the field that depends on space-time, and I can change the description of my coordinates. So I can, for example, take this ball and rotate it in space. Right? So those are external symmetry transformations. But you also know, because you've gone through all these courses of quantum mechanics and quantum field theory, you know that a lot of the interesting stuff that happens in nature is internal, has to do with these quantum numbers and this internal behavior of our fields. Think, for example, of spin, which has a good intuition built on, okay? So there are also internal transformations that can be applied to fields. For example, spin is one internal degree of freedom that we can apply on some transformation over. So what this symmetry, the statement of the symmetry is that if I take a field or a state or an object, let me call it like a bra, no? Okay, a stack it. And I apply a transformation over it, let's say, let me call this transformation U. And the equations of motion, the laws of physics. So where I can measure, where I see, stay the same. Then you declare, if that's the case, you take let's say you are describing a system, measuring things in this system, and you have a good understanding of how it behaves. You have an equation of motion. If you then transform the system and the equations of motion stay the same, then you declare that this system possesses a symmetry. But there is something even more fundamental about this system that you have realized before. Okay, so these symmetry transformations, those are things that we need to do at a mathematical level, because in fundamental physics, we don't think on a ball that is blue and goes around doing the stuff. We actually think on mathematical abstract objects, for example, a quantum state. So we need to think on symmetry operations that are also at a mathematical abstract level. Okay, so symmetries, in the case of, or the way we describe symmetries, is actually in the context of something called a group. Some of you might have had already a group theory course, and if you haven't, it's not a big deal. It doesn't matter. It's just one of the things that you can learn in your last years as an undergrad, right? You can have a course in group theory. What is group theory? Is an area of mathematics that talks about a set of groups and the behavior of these groups and their transformations. For physics, we don't care so much about any kind of group and any kind of mathematical group theory description. We often do care about Lie groups. Okay. This group theory and this Lie groups description allow us to explain and talk about symmetries from a theoretically well-defined way of thinking, right? To have a symmetry, in a way, is to have unification. Unification in the sense that different set of phenomena that apparently they look different, like as I explained before, you're describing a system, then you describe another system, and then you realize that both systems have the same equations of motion. It means that holding the same equation of motion means that those two systems must have something in common. The description must unify in some way. So the concept of symmetry is linked to the concept of unification of phenomena that apparently looks different, but actually they are related in some more profound way, okay? So different situations which evaluated under the concept of symmetry and equation of motion lead to the same physical laws. Okay? In special relativity, you were told immediately about this because that was the basis of doing special relativity. The idea that all inertial reference systems should see the same physics. And what they meant by that, and they should all reproduce the same equations of motion. The equations of motion, remember, they tend to be differential equations. So as you know, in different inertial reference systems, it's true, each reference system, let's say each observer with their ruler and their watch, are going to observe different distances, different movements, different times, and so on. But what unifies all of them is the fact that the final equations of motion need to be the same. The laws of physics are going to be the same. So in special relativity, you already had and as an introduction, as really the thing that settles what are the special relativity equations, is precisely the concept of symmetry. In that case, the invariance under transformations of observers that are inertial with respect to each other. Okay, but this goes much beyond all this. Okay, so the symmetry transformations, the possible transformations you can apply to an object, form this group, the concept of group that I'm going to describe in a second. Okay, so groups I have a very clear mathematical definition. I'm going to spend like 30 seconds explaining what is a group. Let's say a group is simply a set of elements. This set of elements can be, just a few, A, B, C, and so on. This group of elements in a transformation between those elements that satisfies, or you want a way of linking these elements. Let me call this a multiplication. That of course doesn't have to be multiplication as we do when we are children, but just a rule that goes from one element to another element. So this multiplication rule that takes one element, A, and another element, B, and with this multiplication rule, we get a new element, which we can denote as AB. Okay, a way of transforming elements. These elements with this rule of transformation are considered a group if they have very simple properties. One is closure. Closure means that if for all A and B that belongs to the group, let me call this G, then the element AB also has to belong to the group. Essentially, that if I take two elements and I apply multiplication to them, that new element has to be inside the group as well. That makes sense. You should not get out of your group. There's associativity, which simply says that if I have three elements, A, B, and C, that belong to the group, then doing first B, C, and then multiplying by A should be the same as doing first A and B and multiplying by C. All these things are obvious when you think of multiplication as multiplication, but they are not so obvious when you think of more generic structures. Associativity is a property. Then you also need a unit element, which means that there must exist an element E. Let me call this unit element that belongs to G, such that, for example, this unit element multiplying any other element of G in any way, in one way or another, that brings you back A. This again is quite straightforward. And also the fourth condition for this group and this transformation rule, this multiplication rule, to be a group, to be considered a group in mathematics, is that there must be an inverse element, so that for all elements A, there must be an element which I call A minus 1, but an inverse element such that A minus 1 leads you to the unit element. Since I imagine many of you have probably heard about groups before, I don't want to get into a lot of details, but there's a well-defined mathematical structure that is called a group, and these are the structures, the generic structures that we'll talk, or we describe symmetry transformations in the standard model. All right. So in general, one thing I haven't said, and you probably expected, because if you think of multiplication, this is what you expect, is that there is, and there could be a property of commuting. So it could be that if I take two elements, A and B, that this taking B and then A is the same as B, or A and then B, right? So A times B is the same as B times A. This doesn't have to be the case. If it's the case, if you have a group of elements with a multiplication rule that satisfies this property, only in this case you call this group abelian. But many groups in the standard model, many groups of symmetry are non-abelian. Many of the, for example, SU2, SU3 are non-abelian. And what it means is this property is not true, that you cannot take one element and another, and that is the same as interchanging them. This is not going to be the case, and then it's called non-abelian. Okay. So in the context of the forces of the standard model, this famous line of SU3 cross SU2 cross U1, only the U1 is an abelian group of symmetry, and SU2 cross SU3 is a non-abelian group of symmetry, and it has consequences in terms of how it behaves and the interactions. For example, confinement is related to that, okay? So apologies for, probably this is something that goes a bit beyond what you will do usually in this kind of courses, but it's important just to realize that the concept of group is a simple concept. If you haven't been introduced to it, doesn't matter. It's just a set of elements, what you want to consider as your physical objects, and transformation properties among these physical objects. And if they satisfy a set of rules, then these transformations can lead to asymmetry. And if not, then you cannot build asymmetry from them. Okay, so some examples of symmetry groups. So one is the group of integer numbers, 1, 2, 3, under a rule of transformation, which is addition. So you take the you take the group of integers, and the rule that you're going to consider is addition. This is going to be a good group. And on top of that is an abelian group, because you can sum one way or the other, as you know. But this is a very simple one. But for example, you can think of a group of permutations of n elements. This is usually represented by a big pi of n elements. And as you know, the different permutations that you can do of n elements is it has an order. There are only n factorial ways in which you can do these permutations. But something even closer to home, let's say, or things that we actually do in particle physics all the time, is the group of translations in d dimensions. So you think about dimensions of a space-time and d of them. Say just take Euclidean space-time, and then you think about translating, shifting by a finite value any kind of these different positions in this Euclidean space. The elements of that group are those positions. So you see the positions of a space-time. These elements are not discrete. you have a position that is a continuous variable. And the transformation, so it is always the elements of the group and the transformation I'm considering. The transformation in this case is shifting it by a value. This is the transformation I'm talking about. So this shift in this Euclidean spacetime, this multiplication property is a group because it has all the properties that you will expect. There is, if you take one position and shift it by a value A and then B, is the same, this new position is still a position, so it's still an element of the group. Of course, there is a unit element, which is do nothing, so shift by nothing. There is an inverse element, because if I take the position and I change by A, I can always change back by minus A and get back to the original position, and so on. So intuitively, it is easy to see that this group of translations in, let's say, D dimensions are a group where I can think about these transformations, translations in space-time, as a possible symmetry that I can consider. Okay, but there are, of course, counter examples. For example, you think on non-groups, you could think, and again, the group Z of integers, but instead of under addition, I can consider the transformation of multiplication. Why this is not a group? Simply because when I think about multiplication, this n, the inverse 1 over n, right? So that when they are multiplied, they give 1. This is well defined, so there is an inverse. But what about n equals 0? So for n equals 0, 1 over n is infinite, and by definition, this is not in the group of integers. So you see, many things, many situations that we think of since primary school up to particle physics can be considered as elements of a group, something we want to describe, and properties or transformations about these elements. And many of those can end up being a group that describes symmetries that we can then consider as potential symmetries of nature. And, in quantum mechanics, you've seen that as well many times. For example, in quantum mechanics, you were thinking of states, right? And for example, you could think of a state, a cat like this, and that could be, I don't know, it could be, an atom in a particular state, or an electron with a spin up, or something like that. So you think on this state, and you were told that to describe the time evolution of this state, you could do that with these unitary operators, right? And you were told that these unitary operators that describe the time evolution of simple states with definite energy, this will be given by the Hamiltonian. So the Hamiltonian determines the time evolution of your states. So what you were doing is to say, well, I have a state, psi, at t equals 0, and if I want to know what is the behavior of psi at any other t, I just have to take, in this case, the energy of this state, and I know how it has evolved respect to the time equals 0. Okay, so you already in quantum mechanics, you were doing let's say, more bottom-up approach. You were describing states and, if you want, transformations of these states. In this case, there are transformations as time progresses that are described by the properties of your Lagrangian or your Hamiltonian. Okay.
Veronica?
Yes.
There's a question. Is closure easy to prove for translation group?
Is what?
Closure.
Sorry.
Closure.
Ah, very good. Yes, so closure is that any element, remember, closure means that if you transform your state, that new transformed state is still an element of your group. So for translations, what you think is your group elements is all space-time. So any translation that you do on any point of your space-time has to be in your space-time. That will be closure in that context. So as long as your space-time is infinite, you consider the whole space, then yes, you can, closure is there. I don't know.
Yeah, I think that you answered the question. In case, I'll let you know. Thank you.
Cool. So, good. So we've been going through the standard model is a paradigm that we know is incorrect, but yet it works very well and is very robust under, precision measurements that are being done everywhere in the world. So what is so special about the standard model? Well, it's not simply plotting something about particles and interactions and that's it. There is a structure behind that maintains it strong and maintains it consistent. Mathematical consistency is very important. And this is based on symmetry principles. So far we've seen that symmetry, in order to describe it, you need something abstract as well, which is a mathematical group. I've told you a few examples of mathematical groups, and what you need is a group of elements. It can be a space-time, it can be the internal symmetries or the internal space of an electron in spin, for example, or it can be anything, permutations, elements that you do a permutation. And then you need a transformation, a way of transforming from one point in that group to another point in that group. And if they follow a few rules, 4 rules, they are considered a group. And those groups are interesting because they are potential symmetries that we can look for in nature. And I'm also I'm telling you that in quantum mechanics, you've been also talking about states, group elements, and transformations, which is this time evolution. So there is a symmetry behind as well, and so on. So another concept I want to give you before we finish this class today is the concept of representation. So we can do it with any type of group and any type of multiplication rule. But let's do it with, let's say, this one. Let's take this group of permutations. Just, it seems pretty simple. No, we are just talking about take few elements and then the transformations I'm going to consider is that permutations around them. Let's take the simplest case, which is I take 2 elements, A and B. I will also need a unit element, let me call it E. And what I want to do is to do permutations among these 3 points. The group of symmetry that describes these permutations is called Z3. Now, you already, in this group of people, you've already been doing some kind of flavor physics or trying to explain mass hierarchies, or even sometimes when you try to do dark matter models and their stability, you probably heard about these Z groups. Those are finite groups of symmetry. So instead of being like in the Euclidean translations, I can do a translation that is this big or this big or this big or this big. I don't have a, let's say, it's really a continuous parameter that I'm able to vary. And my space of my group is made of infinite elements because it's all space-time and with all the possibilities that it has. There are simpler groups, simpler conceptually, in which your elements are simple. Let's say Z3, you have 3 elements, and you simply want to rotate them. To not rotate them as rotate them, but really go from one to the other, to the other, to the other, and so on and so forth. Permutations. So it's a finite group. The group is made of 3 elements, E, A, and B. Just to make it a bit interesting, we put 2 elements. we can describe the group simply by saying the way they interact with each other. So I put the three elements, and I say under these permutations, the behavior they have. So E with E has to be E, that's the unit element. E with A has to be A, and with B, the same A and B. And then we only are left with the possibilities of these two. And what is going to happen is that when A gives A, sorry, A with A is B, A, B, A. Okay, sorry, what am I doing? E, exactly. E, B with A. Sorry, I'm getting confused. Essentially, E acting on A or B has to just lead to exactly the same, and B on A has to lead to E, and E on B has to lead to A. Ya está. Let me do it in another way. Maybe this is not so easy to see. But for example, if I do A, B, and E, essentially I go and rotate from one to another. Another representation of this three group will be a representation of the roots of Z, a complex number, to 1/3 equals 1. This equation, which is a equation where you try to solve for Z, admits three solutions, which are Z equals 1, exponential of 2i pi over 3, or exponential 4i pi over 3. And you can represent these three solutions in the real part of Z or the imaginary part of Z as being, this is one solution, here is one. This is another solution, this is A. This is precisely 2 pi, this guy over here, and this is B. So you see in the space of complex numbers where I project the real and the imaginary part, my three solutions of that root equation are precisely these three. Or, for example, I could find another representation of Z3 as a way of representing, let me call this way of representing, the unit element is a matrix unit. So 0, 0, 0, 0, 0, 0. The way of representing A could be another matrix, 0, 0, 1, 1, 0, 0, 0, 1, 0. And the way of representing B could be yet another matrix, 0, 1, 0, 0, 0, 1, 1, 0, 0. Okay, so let's recap. You might be wondering, why am I doing this? What I want to show you is that even in this very simple situation where you just have 3 points and you want to consider permutations among these 3 points, if you put these points in a triangle and you start rotating this triangle, just changing one point by another, this is intuitively, you have the view that this is purely a symmetry, in the sense that if you didn't put labels on the points, you will get the same triangle in exactly the same orientation, right? So those final permutations probably do represent a symmetry, and they do. The only thing we need to do is to identify one element as the unit and the other two to have the proper transformation properties respect to each other. Now we have other ways of representing exactly the same situation. We find these Z3 properties among the solutions of an equation that we try to solve. So Z to 1/3 equals 1. The three solutions that are obtained when represented in this plane of complex real versus imaginary, they also form this triangle. And you know that you can simply rotate a finite amount, A, B, and 1, and you go from one to the other. So that's another representation of exactly the same behavior. But you could also represent this Z3 as the properties that are formed by these three matrices and the possible, under the operation of multiplication of matrices. So indeed, if I multiply D of E, or the unit element, over D of A, I get D of A. So the action of E over A is indeed giving me back A. The same for B. You know, and when I do A times B, I recover E, and so on. So I get, this is another way of representing exactly the same kind of Z3 symmetry. Seems like a long explanation for something that, you know, is kind of obvious. But I really want to make this point, is that when you can describe one symmetry in a very generic form, say my symmetry is acting on a group of elements with a given multiplication rule. But there are many, in general, there are many possible representations of exactly the same symmetry. So you might find sectors, let's say, of particle physics or crystallography, or sectors, you know, of other areas of science, where exactly the same symmetry is realized, is manifested in different ways. And only under the concept, the abstract concept of a symmetry group, then you realize that you are actually talking about the same thing. So again, different representations allow us to describe the kind of physics we are dealing with. But once we discover that there is a symmetry behind actually acting on this or ruling the behavior of this system, we can start finding connections among sectors that didn't seem to be related at first sight. And it's this concept of representation that is quite important. Okay.
Veronica, there's another question.
Yes.
How do these matrices come from?
So I decide because I want to represent.
Yeah, I think that they refer to the DE, DA, DB.
Exactly. Let's say that I want to find me. I decide that I want to find a representation of this Z3 as a matrix representation. And I want to do it in, let's say, in 3x3 matrices. You are going to see that this is what we do. We decide to represent our symmetry transformation in many different ways. So I decide that the only thing I need to do is to make sure that I actually end up with this composition rule. Okay, so that when E acts on A, it gives me back A. The same for B. Then when B acts on A, it gives me back the unit element. So A and B are inverse of each other. So I need to find A and B, the representations of my elements A and B, that satisfy these kind of rules. And then you don't have that many options. So the simplest thing is to decide that E is going to be the diagonal. That makes it very simple. No matter what A and B I decide later on, these two properties will always happen. And then it's up to me to find two matrices that when I multiply them, A and B, gives me back the diagonal. It's not unique. I could find other options. But that's precisely the thing. I want you guys to realize that we define a group as you do, set 3, set n, whatever, and the representation of this group is it has lots of arbitrariness, lots of variety and diversity that you can choose from, so that you can adapt to your situation. Depending on what kind of physics you are doing, your objects will be different, your group elements will be different, and there will be better ways of representing this symmetry transformation. So in this sense, here I just built it out of knowing that I need to reproduce this transformation here. Okay.
There's a question.
Yeah, cool.
I read it for everybody, but I also write it to you, so it's easier to understand it. Is the rule which defines like A acts on B gives A while A acts on a given E and so are given? What exactly are A, B, and E? Are any integer?
They're objects. They're nothing. They're anything. Okay, so A, B, and E can be anything. Can be 3 balls. They can be, this case, A, B, and E. In here, I'm just describing them as 3 points in space. Here, I'm describing them as a representation of the position of a complex number in the complex plane. Here, this matrix, the diagonal, or these other metrics, are representing A, B, and E. So precisely that's the thing, that they don't have to represent, they are not particularly anything. They are just group elements defined in the most generic way and possible permutations that I can do in these 3 group elements. So in order for these permutations to be a group, then a possible symmetry that I can apply and think of, they cannot be anything. They have to follow some transformation rules where you get closure, where you get inverse, and when you get unit element. So this representation does satisfy this, right? The unit element is this guy. And if I multiply these two, I will get one or the other. So I get the unit element. This by 1 gives me the same element, and so on and so forth. So this representation does work. And this representation of exactly the same phenomena, the same abstract phenomena, a property of permutation, does work as well. So later on, we are going to talk about symmetries that affect, for example, fields, fermions, scalars, vector bosons. And there you will have a better grasp of what we are talking about. But basically, I wanted to have this first lecture to talk about symmetry groups in general, because all this behavior is very generic. It applies to particle physics the same way that it can apply to properties of certain galaxies, or it can apply to crystallography, or it can apply to systems that are self-similar, and so on. Many areas of physics and of science relate thanks to symmetries. From now on, all the applications I'm going to give are going to be in particle physics. So fear not, I'm not going to get into super abstract stuff, but I wanted to give you at least one example of one very simple symmetry, discrete, with finite group, and that can be represented in the ways I've shown and many more that you could imagine. Okay.
There's another question I just wrote to you, but just to know to everybody, this student is asking whether in the submatrix should be BE EA instead of EA AE.
See, you mean here over here?
Yeah, exactly. I think.
Yeah. So yes, A and B. In this case, you remember the group has to have a unit element. We know AC. but also has to have an inverse element so that when A and B talk to each other, yeah, so you're right, whoever the student is. So when A and B talk to each other, they actually lead to E things, right? And when A and A talk to each other, go to B, and B go to A. So that's the correct one. Thanks. I don't know who asked the question, but yeah, that's correct. Fantastic.
And
okay.
Still another one, maybe the last one for, maybe the next to last one. So what is the result for dA times dA as the table does not resemble which set of equations?
I guess now that it has been corrected, is you can check that, you can multiply them.
And check it explicitly, yes.
Yeah. And the last question?
The last question refers to the action, so maybe you can finish what you were saying and let's go to the last question.
Yeah, I guess the next thing I wanted to tell you is once we have finished this, let's say, very generic description of a possible group and different representations, I wanted to tell you that in physics, particularly to describe forces, we will consider groups are called Lie groups. So I just wanted to give you a short introduction on that. So you want to ask the question of the action? So I don't see, no?
Sure, I just wrote to you. The actions might be extrema by principle, but why for symmetry in various action initiation taken at minima rather than maxima?
Yeah, we know that it has to be extremal, no? But we also, you know that, yeah, very good question. So I was talking about how there is this concept of action. You probably heard about actions if you did quantum field theory, because nowadays we just go to Feynman diagrams and we start computing things, and there is a set of rules of how to, let's say, optimize this kind of quantum calculations, right? But probably also when you started quantum field theory, you were told about the different ways in which quantum field theory was introduced and developed. But this is not so much to do with quantum field theory. In fact, it is something that applies to when you do thermodynamics, classical field theory, and so on. And it's the idea that indeed the behavior we see and the probability we associate to a particular behavior is related to this, the fact that we want to minimize the action, that we think that the main object in nature is this exponential of minus s. If you, among you guys, you work on lattice, you probably see this because that's your starting point. This action and this exponential of minus s. Okay, so you believe that your exponential of minus s is the important thing, then you, of course, you want to get to the minimum of that guy. This, whoever asked the question, the student, yes, you're right. So the delta s equals 0 means I need to find an extremum, like a maximum or a minimum. But we know that the higher probability is associated with the minimum, not with the maximum. That again depends on the kind of physics you are doing. If you guys are working on cosmology, sometimes you actually want to consider a different situation where you look to extrema that is actually maximum. But for most of the applications we do, and for the standard model, you want to find the minimum, because there is where your higher probability is associated to.
Okay.
Okay. I guess we shouldn't go much beyond this. No, it's 11:35. Luca, is okay if I take 5 minutes to talk about Lie groups, or should we?
There has been a presentation in the beginning, so you still have 5 minutes without any problem.
Sounds good. So I'll do that. So this way, tomorrow we can already start, just particle physics and nothing else. So Sorry, too many. Sometimes what we want to do when we do transformations, this multiplication in human property, we want to consider elements of our group that are not just one element, let's say 1 point, but are actual elements that depend on a parameter. Let me call this a parameter alpha that is continuous. And what we want to do is actually consider small variations respect to this parameter. So if you want, in my space of possibilities or elements of this group, I want to consider an element G, let's say of alpha equals 0, and I want to see what happens if I move a bit around this element alpha equals 0. So G of alpha, but now with alpha very small. In other words, sometimes what I want to see are properties that are local. Local meaning short range, meaning that are close to the original element. I want to see how these properties change as I vary a tiny bit. This makes sense, right? Because you guys are used to do quantum mechanics and quantum field theory. You think about the properties of a field at a given position, and you want to see how these properties change as you move a tiny bit in this position. You want to understand local properties. Those are very important because we know through causality and so on that the local properties of a theory are very important. Usually when you do quantum field theory, you want to think about situations where the physics does not change dramatically as you move a tiny bit in space-time. On the contrary, you want something that is smooth. In physics, usually we want things that are smooth, and this concept of continuity and smoothness is very important. We don't abandon this concept unless something dramatic happens. For example, if you are examining any physical parameter, you usually assume that as you vary this parameter, the changes are going to be small. If the parameter variation is small, the changes will be small. Except, for example, if you think about phase transitions, there are situations where, as you vary, for example, the temperature, or in a ferromagnet, you are changing a bit the magnetic field or so on, you suddenly, with a small variation, you cross a boundary and then you change phase. But those are very specific. Phase transitions, critical phenomena are very specific things. In general, you know, if we think about the Large Hadron Collider, or we think about quantum field theory and computations of precision, we are actually going to think about continuous behavior with the parameters of our theory. There is where, among all the possible symmetry groups, we get to a specific type of groups that now vary or depend on a continuous parameter. And those are called Lie groups. Okay? And a Lie group is such that the elements are smooth, and you can actually expand them so that at the beginning they will just lead to 1, so the origin, and then you can actually expand on this parameter alpha. So at leading order you will have alpha, and the first order in your Taylor expansion, let me call this element here, which will be essentially the derivative with respect to the alpha at alpha equals 0, let me call it T, for the reason that will be clear in a second. It's just a name. For the moment, it's just a name, okay? Call it T, and then there will be things at order alpha square. So Lie groups are symmetric transformations where I can actually expand over a parameter, and this expansion is smooth, and meets a Taylor expansion, and so on. And typically in Lie groups, I just care about the first order in my expansion. Okay. And if there are more than one direction in which I can expand, I usually denote this direction with a label A. So for example, imagine that I can go in this direction, or this direction, or this direction, and so on. And hence, I denote this first order expansion with the same label A. Okay. Just possibilities of expanding is, imagine that you're, let's say in space-time, you have a function that depends on 3 space dimensions, x, y, and z, and I could have possible first derivatives respect to x or y and z. So these 3 possible derivatives will correspond to these labels A equals x, y, or z. Okay. So that's there is a whole mathematical theory of Lie groups and so on, that mathematicians love. Okay. And you could also try to represent your function that is smooth and integrable, and at least at first order, you could imagine that approximate this exponential form. You can say that this is, at least at first order, the same as having expanded something that goes as exponential of I alpha A TA. Okay? So this is called an exponential form, and that gives you a finite transformation. So for any value of alpha, big or small, I can make this transformation. I can represent transformation this way. But in particle physics, we don't care so much about symmetries in general. We actually care about symmetries that depend on a parameter, and we want to examine the local structure, so the very close by structure. So we really don't care so much about this exponential and all these possibilities that it spans. We actually care a lot more about this part over here. The first deviation, the first closest thing that you can find. Okay, so what represents the way this group actually acts is not so much this exponential over here that can be quite complicated, but actually the behavior of these TAs. Here I'm probably going to make connections with what you've seen before. From Lie groups and from this kind of representation, you can define something that is called a Lie algebra. And what this Lie algebra just tells you is the following: is if you have this TA, which is, remember, it's like taking different directions of possible transformations. TA could be Tx, Ty, Tz, or it could be in an abstract space. One important property that determines the local behavior of your transformation is actually understanding this. When I take a commutator of 2 of these TAs, what it leads to. So one thing we do know, because a Lie group is a symmetry group, so it has this concept of closeness. So any transformation has to stay inside the group, is that this Lie algebra, when I ask myself the question of what does this commutator give to, what it has to give is another element of this algebra. Since it has to give another element of this algebra, I can define, and this is me defining, I like to put an I in front for, again, normalization, and I'm going to evaluate all these commutators that will depend on the value of A, of B, and C. Once I know for a group of symmetry, what are the possible TA, B, C, or all these T's, all these first approximations of my Lie group, and I know how they commute with each other, I can evaluate all these F, A, B, and C. They are just numbers. They tell me when I take T1 and T3, what gives me, and so on and so forth. Once I know this, these are called structure constants. I should stop now. Structure constants, and they determine the Lie algebra. This, again, seems to be far removed from probably the things you've seen so far. But these structure constants, This Lie algebra is going to determine the way these symmetry groups behaves, is going to be our way into describing the forces of the standard model, the behavior of gluons, photons, W's, Z's, and so on, only going through these structure constants. But now I'm going to stop here, and this is what we are going to do tomorrow, to discuss all these things. Okay.
Thanks a lot, Veronica.
Thank you, Luca. Sorry for the delay.
It's fine, perfectly fine. We had the opening of the school at the beginning. Is there any question? I don't see anybody writing, so I think we can close here and let's see tomorrow. Thanks a lot.
Bye-bye.
Bye, Veronica. Thank you.